as the light hits the silvered part, when the light hits here, what will be the angle of deviation? And the answers are given: 90, A 90, B 180, C 120, and D 45. Okay, this is a glass slab. It's like just like this. The only difference is that one part of it is coated. So when light is incidented at one end, this side is coated. So because this is air glass, it will hit this bend and then hits the coated other side. Then it will reflect. Then we are looking at for the angle of deviation after the refracted ray hits the silvered parts of the slab or of the prism. That is. So I want you to give it a try for 5 minutes. Please go through it quickly because after 5 minutes, we will discuss it and see how. So I'm giving you 5 minutes to attempt it. Start with. So what will be the angle of deviation? The angle of deviation. It's 1234. So at exactly 1239 or 1250, I'll come 40, I'll come your way. So 40. So just 6 minutes. The answers are there. So when you get it right, you say it. Let's quickly review it. Please, if you were able to finish, share with us some of the answers or the answer you had. If you were able to finish. Whoever was able to finish, what did you make as your answer? Anybody? Reader, Eurefua and Co. If you were Cadmiel, Calvin, Kweku, if you were able to finish, share your answers with me. Whoever was able to finish. Kezia.
Mercedes is 90.
You had 90. Who else? Who else? Before we all look at it, who else got 90 or a different answer? Calvin, Cadmiel, Kezia. Okay, let's see if it's 90. Once this is a glass prism or slab, and as I told you earlier, the glass slab is just like this. The only difference is that one side of it is coated to look like a mirror. Light is incidented at the other end at an angle of 40. So when you incident light here, because from air to glass, it would bend. It will bend. So, and it will bend towards the normal. So we'll have this. This becomes the refracted ray. So this is R. Now, because this side is coated silver, or is that behaving as a mirror, if this will become the incident ray, so another normal here, and the light would reflect. It will reflect to obey the laws of reflection. Angle of incidence equals angle of reflection. Now we are asked to determine the angle of deviation. So what we mean by the angle of deviation, what it means is that this ray originally is following this path, but by virtue of its interaction with the mirror, its path is changed from this direction to this direction. So it means this whole angle would be equal to the extent to which the ray is deviated. So this angle will be equal to the angle of deviation. Okay. So to determine the angle of deviation, this line is 180. We must determine this angle and subtract this angle from 180 to get the angle of deviation. Please, are you okay so far with the explanation? Class, are you?
Yes.
So this is the angle of incidence. Angle of incidence equals angle of reflection. This is also I. Now, by vertically opposite angle reason, this angle will be equal to this angle. The angle of refraction is equal to the angle of incidence. So R would be equal to I. The reason is vertically, alternate, they are alternating. Because of alternate angle rule, alternate angle rule. So the moment I'm able to find R, I have I. Because I is equal to R, knowing R will help me determine this angle. Okay, so we use Snell's law. The refractive index, instead of using Snell's law, let's use the product of the refractive index. This is air, glass. So the refractive index of the first medium, air, times the sine of the angle of incidence there, 45, must be equal to the refractive index of the second medium, which is glass, times sine of the angle of refraction. We can also use Snell's law for absolute refractive index. Sine I on sine R, the value is the same. Since this is air, the refractive index of air is 1. So we have sine 45 equal to the refractive index of glass is given as 1.5 times the sine of the angle of refraction, which we don't know. Therefore, sine R will be equal to sine 45 over 1.5. If we use Snell's law, the absolute refractive index of glass is given as 1.5. So 1.5 is equal to sine I. I is 45 over sine R. Therefore, when we make sine R the subject, sine R is equal to sine 45 on 1.5. So whichever way you want to go, the value is the same. Okay. So use this to help me get the value of R. Calculate the value of R for me, class. Sine 45 is root
28.
approximately 28. Thank you.
21. Yeah.
0.1. So if R is 28, then angle of incidence will also be 28. Angle of reflection will also be 28. So this whole angle will be equal to, so the angle of deviation will be equal to 180 minus 2 times 28. Because this whole angle here is equal to 2 times 28, or 28 plus 28. And what is 180? This is 56. When you subtract 56 from 180, what's the answer?
1, 2, 4.
So approximately the answer is to the nearest, angle, which is 120 degree. To the nearest angle, that will be 120 degrees.
Mr. Edia, please, why didn't we use like just 180 minus 2i?
Oh,
Like, why didn't we use that formula?
we could have used it. You see, it's the same.
But you not get the answer.
Pardon?
If you use the 2i, you take the I to be 45. Then you
No,
get 90.
no, no. 2i.
Okay.
This is, look at when you have to use 180 minus 2i. This is a mirror. Normal. Angle of incidence. Angle of I. So if it is going here, then if you want to determine this, we have this as the angle of deviation. This will be equal to 180 minus 2i. The reason why we did not use this direct is that, you see, this is a mirror. This one, the ray is being refracted, and after that is being reflected. So you must find R. It is not the same as this one.
Okay. Yes, please. I understand.
Exactly. So that's it. That's it. Okay. So please, is everyone okay with the solution? If you have concerns, let me know.
Yes, please.
Where? Mamia?
I don't have any concern. I'm saying that I understand.
Okay. So please, you see, when the question is given, it's not difficult, but take your time to analyze, apply the concepts, listen to the question, and apply whatever is said. This one is being refracted, and after that is being reflected. Okay. And the good thing is that if I know these questions are a bit challenging, yes. So as I take you through this, when you get easy questions, trust me, you will see it yourself. Another question. Right? Put down this question for me. If the speed of light in ice, if the speed of light in ice is 2.3 times 10 to the power 8 meter per second, if the speed of light in ice is 2.3 times 10 to the power 8 meter per second, what is its index of refraction? What is its index of refraction, meaning the index of refraction of ice? Then B, what is the critical angle of incidence for light going from ice to air? B, what is the critical angle of, what is the critical angle of incidence for light going from ice to air? I repeat, if the speed of light in ice is 2.3 times 10 to the power 8 meter per second, what is its index of refraction? The index of refraction of ice. And B, what is the critical angle of incidence for light going from ice to air? So 5 minutes. Make me proud. 5 minutes. If the speed of light in ice is 2.3 times 10 to the power 8. So speed of light in ice, 2.3 times 10 to the power 8. What is the index of refraction? I think, sorry. This one is so simple because we learned that absolute refractive index is equal to speed of light in air over the speed of light in a medium. So here, speed of light in air against speed of light in ice. So this is a straightforward question. And speed of light in air is 3 times 10 to the power 8 over 2.3 times 10 to the power 8. Therefore, this is 3 on 2.3. What is 3 divided by 2.3? What answer did you make? Those of you who got it right.
1.3.
Okay, so 1.30 is the index of refraction of ice. Then the next question, what is the critical angle of incidence for light going from ice to air? Okay, ice to air. You know, for total internal reflection, you must first have the critical angle of the material. So, and when the light is moving from, the condition is that light must move from a dense medium to a less dense medium. So dense medium to air, we saw yesterday that the sine of the critical angle would be equal to 1 over the absolute refractive index. Therefore, C, which is the critical angle, is equal to the sine inverse of the absolute refractive index of the material. Okay, and this is 1.30. So what is the sine inverse of 1 over 1.30?
50.28.
50.28.
So that's the critical angle. How many of you got everything correct? Please up, show by hands. Okay, Elizabeth got it. Mamiya got it. Eurefa got it. More hands. Oh, my gentlemen, let me see your quick. Who got it? Who else? More hands. Kezia. Okay. All right. Thank you. All right. Another question. Another question. I think I have the diagram here. No, I doubt. Okay. Let's quickly put down this question. Light is refracted from material 1. Light is refracted from material. Let me take a shot and then drop it in the group rather for quick review. Let's solve the question together. So we are given 3 composite material. Three material.
Heck no.
Three
No.
material.
No.
Leonard. I beg
Sir.
you, mute yourself for me. So we have first material. Okay, so this is material 1 of refractive index 1.6. This is material 2 of refractive index 1.8. This is material 3 of refractive index 1.3. So this is the first one. Now, a ray of light is incidented in material 1 at an unknown angle theta. The question is that, what is the angle theta? So we are first and foremost asked to find the angle of incidence within the first material. Okay, nice question. You see, as it looks, I'm sure you think that the thinking is that it's a very tough question. No, it isn't. Let's pick the information given. It said in the figure, light refracts from material 1 into a thin layer of material 2. So the light is refracted. Now it is refracted because material 2 is denser, has a higher refractive index 1.8 compared to material 1. So it will bend. Okay, it will bend. If it will bend, how will it bend? Towards the normal, because it's from less dense medium to a more dense medium. So it will refract towards the normal like this. Let's continue. And then it's incident at the critical angle on the interface between material 2 and 3. The interface between material 2 and 3 is just the boundary between them. There's the boundary or the interface between material 2 and 3. And we are told that it hits the critical angle. Now, class, if the light ray hits the critical angle, okay, what will happen? If the light ray hits the interface or the boundary between material 2 and 3, and it hits the critical angle, what do you think will happen? Yes, let me pick your views.
Please, there'll be no refraction of light.
We are told that after this being refracted, it hits the interface between material 2 and 3 at the critical angle. So when the light hits the critical angle, what do you think will happen?
It will produce an angle of refraction of 90
Exactly.
degrees.
In material 3, because
3, yeah.
the condition is that for total internal reflection, light must travel from a more dense medium to a less dense medium. So the refracted ray is from a more dense medium and entering into a less dense medium. Now it is hitting the critical angle. So once the ray hits the critical angle, it must produce an angle of refraction of 90 in the less dense medium. So what will happen is that the refracted ray will just be on the boundary or the interface between material 2 and 3, producing an angle of refraction of 90. Please, is it understood? So it it isn't a tough question. And this is what we need to solve the question. Now we have to find theta. Let's see how we can find theta. In determining theta, if you pick the product of the refractive index of the first medium and the sine of the angle of incidence, theta, it must be equal to the product of the refractive index of the second medium and the sine of the angle of refraction. Okay, here we don't know. So let's represent that by C, because this angle would alternate with this. So C. Okay, once what we have here is like this. There's the normal refracted ray, and then the other normal. This angle here would alternate with what is here. So if this is the angle of refraction, the angle of refraction here would be equal to the critical angle. So R and C. R will be equal to C because they alternate. Okay. N1 is 1.6 times sine theta. N2 is also 1.8 times sine C. We don't know sine C yet. But we can also apply the same concept to medium 2 and 3 to find C. And that is N2 times sine C, N2 times sine C must be equal to N3 times sine 90, because we know the angle of refraction here, that is 90. Knowing N2, knowing N3, we can find sine C. So 1.8 times sine of the critical angle is equal to 1.3 times 1. Sine 90 is 1. Therefore, help me find C. Sine C will be equal to 1.3 over 1.8. What will be C? Help me determine the value of the critical angle C. I'm leaving that calculation to you. Please finish it and then tell me the final answer. Kelvin, Mamiya, Erefua, Rida, Kezia, what will be the value of C?
46.2.
46.2 degrees. Okay. Now, if this is it, then use this equation to find theta for me. We have C. We have C now. So substitute it and help me determine the value of theta. Okay, so just give me the value of theta straight away. What have you made for theta?
54.29.
54.29. So approximately 54.3 degrees. That's it. So simple, not difficult at all. The next question, if theta is decreased, listen, if the angle of incidence theta is decreased, is there refraction of light into material 3? If we decrease theta, will there be refraction of light into material 3? Look at it and then tell me. Just put some calculations down and then tell me. In fact, if you give me your answer, I will ask why. So think of your why in giving me an answer. If theta is decreased, is there refraction of light into material 3? 3 minutes. Put calculation down and then give me your view. And also, are you there? Safo?
Yes, please.
Okay. Eva, are you there? Or Eva is not in the building. Yes, who is ready to answer the question? Who is ready? Free will. Just avail yourself to express your view. Who is ready? If theta is decreased, is there a refraction of light into material 3? This is yes or no, but you must be ready with your supporting statement. Why do you think it will be yes? Why do you think it will be no? Who is ready? Oh, this is free will offering. Oh. Cadmiel, share your view with us. Angel, are you here? Cadmiel. Okay, au revoir.
Mr. Dear, please. There will
Au revoir, I'm listening. If I is decreased, will there be refraction of light in material 3? Oh, but Erevo, I'm not hearing you.
there will be
Why do you say so?
because As you decrease I,
Mhm.
R will also, let me see. It will keep moving. R will keep moving away.
So
So
will R also increase or decrease?
it will increase. R will increase when you decrease the I. Oh, I think so.
Did you calculate it? Because
No, I'm still on the calculation.
okay. So the trick is that decrease theta. Okay. I is actually the value of theta. So as if theta is decreased, okay, is there refraction of light into material 3? So the value of theta is 54.3. Decrease it, calculate for R. Don't forget R is also equal to C. The value of R or C will determine whether there will be refraction or not. Mamiya, what were you able to produce? What were you able to derive from your analysis of the question? Oh, Mamiya is not here.
I haven't done any calculation.
Oh, see you. Okay, quick one. So if we decrease theta a little bit, what will happen to R or C? Okay, so I'm decreasing theta to maybe 50. If theta is decreased, so I'm reducing the value of theta to see the effect that will be obtained in material 3, whether total internal reflection would occur. If total internal reflection occurs, then it means there wouldn't be any refraction in material 3. So the refractive index of 1.8. Oh, okay. I must first calculate R or C. So 1.6 times sine of 50 must be equal to 1.8 times sine of R. Leslie, are you here? A lot more of you are not present today. So put this together and then give me the value of R. Multiply sine 50 by the product of this, the ratio of this two for me. Please get involved. Let's look at it quickly. Sine 50 times 1.6 divided 1.8.
.68.
So what is the sine inverse?
42.84.
So R, if we reduce theta to 50, R will be 42.84.
Yes, please.
Okay. Now, don't forget, R will be equal to C. So if theta is reduced to 50, the critical angle will be 42.8. Okay. So if the critical angle now is, or R is 42.8, then it means when you compare this with the original value of the critical angle C, this is less. The original value C we had was 46.2 when when theta was increased. When we decrease theta R now is equal to 42.8, which is less than the critical angle. And if the angle of incidence in material 2 is less than its critical angle, yes, there will be refraction. Okay, there wouldn't be a refraction only when R is greater than the original critical angle, which is 46.2. If this is greater than this, then there will be total internal reflection. But when theta is decreased, R is still less than the critical angle, there will be a refracted, or there will be refraction. So that is it. All right. Then I think a last problem for you. Then good. I've posted a question. I've just posted a question to the group. As for this, I will never. I'll still give you 5 minutes to do it. We have a ray of light incident at glass air interface. So sorry, glass water interface at an angle I. At an angle I. It emerges finally parallel to the surface of water. What is the value of the refractive index of glass? And the answers are given. We have glass, water, air boundary. Light is incidented at an angle I. The angle of refraction in the water. So it is incidented from glass to water. Angle of incidence I, angle of refraction R. When it emerges out of the water, it makes an angle of refraction of 90 degrees in the water-air boundary. Jesse, please mute yourself. Given the absolute refractive index of water as 4/3, what will be the refractive index of glass? A, B, C, and D is given. 6 minutes. 6 minutes. I want to see how you can think through this. We have solved a similar question, so please try it. Try and then get it right for me. Very, very similar to what we've just solved. Hey, Julian, you are here. And you've been silent. Eh? Kweku, Casey, are you too? As for Leona, these days, you don't even call. Is somebody true? Is somebody true? If you are true with, or if you've managed to get one of the answers, let me know. We have the possible answers. The first answer (4 on 3 sine I). A, 4 on 3 sine I. B, 1 on sine I. C, 4 on 3. And D, 1. Arif, are you true? Arif, Mami ya.
No, please.
Mami ya.
No, please, I'm not through.
Kezia. Kelvin. Julian. Nana Safo. Julian, what did you get?
Sorry, I'm not done.
Oh, it's a simple question. Okay. It's a simple question. We are looking for I. So what will be, okay, the refractive index of the glass. What is the refractive index of the glass? Now let's see. If you pick refraction here, the product of the refractive index of this medium, water, and the sine of the angle of incidence, which is R, and I'm moving, the direction of the light follows that of I. So I is refracted, hits here, and then meaning R is equal to C, the critical angle. The reason for which the angle of refraction in air is 90. Okay. So if we take refraction, sorry, deviation of light here, the product of the refractive index and the sine of the angle of incidence here must be equal to the product of the refractive index of air and the sine of the angle of refraction, which is sine 90. So the refractive index of water is 4/3 times sine of R. This is equal to 1 because refractive index of air is 1. Sine 90 is also 1. So everything there at the right hand side is equal to 1. Therefore, sine R is equal to 1 over 4/3, which is equal to 3/4. So we have sine R to be that. Let's leave our answer as this. We have sine R to be 3/4. Please, are we okay here? Are we okay? Give me feedback.
Yes.
Yes, please.
Okay. Then let's pick deviation of light here. The product of the refractive index of the first medium, which is glass, and then sine of the angle of incidence, I, is equal to the product of the refractive index, okay, by sine R. And this is what we are looking for. But the refractive index of water is 4/3. So 4/3 times sine R. This is what we got for sine R. 3/4. So this is equal to 1. Therefore, the refractive index of glass will be equal to, when we divide through by sine I, so 1 over sine I. So the answer is B. The answer is B. Class, is that understood?
Yes, please.
I beg you, take your time, analyze it bit by bit, and it will be solvable, okay? It will be solvable. Okay. The last question, I know I'm torturing you with problem solving, but forgive me, it's necessary. The last one I want us to tackle is this. The last question I want us to look at is this one. I think I forwarded it. Good. I'll solve it with you. Good. So the refractive index of the material of a prism is 1.6 for a certain monochromatic ray. What should be the minimum angle of incidence of this ray onto the prism so that the total internal reflection occurs? So that total internal reflection occurs when the ray leaves the prism. When the ray leaves the prism. Take the refraction angle of the prism to be 45 degrees. Take the refraction angle of the prism to be 45 degrees. So I'm solving this with you. So let's assume we have a right angle triangular prism. This is the base. The angle of the prism we are told is 45. Whether you draw it like this or and indicate that the angle or the refraction angle of the prism is given as 45. Now, light is incidented at one end of it. Let me use this one. This is the normal. This is the normal. I is what we are looking for. Of course, air to glass, so it will deviate towards the normal. Now the question is that, what should be the minimum angle of incidence of this ray onto the prism so that total internal reflection occurs when the ray leaves the prism? When the ray is leaving the prism for total internal reflection to occur, what should be that minimum angle of incidence? So we also know that for total internal reflection to occur, the angle of refraction within the less dense medium, here A, must be equal to 90. So that's the prerequisite. So for total internal reflection to occur, the refracted ray must just be on the boundary, and this angle must be 90. So when we know this angle of incidence within the denser medium, then we can figure out, okay, the extent to go in order to have total internal reflection. We know that for total internal reflection to occur, the angle of incidence in the denser medium must be greater than the critical angle. So if this is 90, then it means this angle here must be equal to C. Please, is it understood? Is it understood here? Give me feedback. Yellow, are you there?
Please come again.
Yes, sir.
You see, we are looking at as at when the light leaves the prism, what should this angle be so that total internal reflection would occur as at when light leaves the prism? Now, the requirement for total internal reflection is knowing C. So for this to be 90, then it means the angle of incidence within the dense medium must be equal to the critical angle. So if this is 90, this will be C. Okay. So
Yes.
at the moment, we need the value of C because that is the requirement for total internal reflection. So the question is that what angle of incidence will give us the critical angle for the refracted ray also to be 90 when the ray is emerging out of the prism? So all that we are interested in is this. Now, this is R1. we are given the refractive index of the material. The refractive index of the material we're told is 1.6. So N is equal to 1.6. So to determine I, we know the refractive index must be sine I over sine R1. We have the refractive index. We don't know R1. Okay, so knowing R1, we can easily calculate for I. So this is how we can determine the refractive index of the material. Now, using A is equal to R1 plus R2, we have A. A is given to us as 45. Okay. Then it means that the critical angle C is equal to R2. Because this is R2. But R2, if this is 90, then R2 must be equal to C. Is that okay? So when we find C, we've also identified R2, out of which we can be able to calculate for the value of R1. Okay, so using sine C is equal to 1 over the absolute refractive index of the material, we have 1 over 1.6. Therefore, the critical angle would be equal to the sine inverse of 1 over 1.6. Calculate this for me. Calculate the sine inverse of this ratio for me.
$38.68.
Come again, 38.
0.66.
Okay, so let's have it as approximately 38.7. So this is the critical angle for which R must be 90 and C is equal to R2. So if C is equal to R2, therefore R1 would be equal to A minus R2, which is 45 minus 38.7. That's the value of R1. So what would be the value of R1 here? When you subtract 38.7 from 45.
6.3.
So 6.3. Please, it's R1, R2 are angle. So then don't take it as length. So if this is R1, then we can easily, with this, you can easily find I. So sine I, which is 1.6 times sine of R1, which is 6.3. When you finish, you take the sine inverse of. Take the sine inverse of it. The answer was indicated in the question. I gave the answer as I is equal to 10.1 degrees. So let's confirm.
Yes, please, it's 10.1.
So that's it. Okay. So for total internal, so this must be the minimum angle. The minimum angle. I would give you a situation where the angle of refraction in air is 90. So knowing that if this is 90, then the critical angle of the material is this. Then it implies that when you increase the value of I a little bit, then you have a situation where total internal reflection occurs. So knowing C would help you determine how to create total internal reflection, because for total internal reflection to occur, the angle of incidence must just be a little bit greater than the critical angle. So we are using C to calculate for I. That is the minimum angle. Please, any question? Any question? All right. I'll give you, I think I've given you a lot of questions in the group, but sorry. Your assignment is the NOVDEC 2024 question on triangular prism. Let me forward that. Yeah, this is the assignment. Having gone through all that we've done, this must be so easy. That's the it's a 2024 paper on refraction of light in triangular prism. That is your assignment. Please take notes. Please take notes. It's a very simple question. We've solved more difficult ones than this one. So I expect each one of you to give it a try, please. Okay. You are giving it. All right. So you are given a triangular prism. The angle of incidence is 30. It's an equilateral triangular prism. Okay. You are to find R1, R2, and E, given that the refractive index of the prism is equal to 1.5. Okay, so that's your assignment. Please take note. This is so easy. All right, so we have about 30 minutes to end the session. Let's end it well. Yesterday, we were talking about some applications of total internal reflection. And I mentioned the prism binocular, the prism periscope. Oh shit. That network has not been so stable. So forgive me. The network has not been so stable. Can you hear me?
Yes,
Yes, please.
So we made mention of the prism periscope. The prism periscope. Then the binoculars. Binoculars. Then the mirage formation. The prism periscope, I gave you the diagram. Within the prism, (45°), this is 45°, this is 90. Okay, so it is arranged, two prisms arranged in this manner. And then the other, this is the design. The other one is designed like this. Now a ray of light hits the upper prism at an angle of incidence of 45. And since the critical angle of glass is 42, ground glass, there will be total internal reflection because the angle of incidence here is 45. The light also hits this at the same angle, 45. Since the angle of incidence is greater than the critical angle of glass, we also have total internal reflection here. So an observer, this is the observer over here, sees an object here, below. So that is the principal design of the prism periscope. Then the binoculars. I think I have a binocular here. Let me see if it's still here. Oh. This is what I was talking about. The binocular. This also operates on the principle of total internal reflection. When you open it, within there is a prism. There is a prism. So I just want to open it for you to see what is inside there. There is a prism. There is an equilateral triangular prism. Okay, our time is already gone. There are two prisms. Equilateral triangular prism like this. Now what happens is that in one of it, light from an object hits it at an angle of 45 degrees, just as this one is. Once the angle of incidence within is greater than the critical angle, the light is internally reflected. So instead of it coming out of the prism, because the light is hitting it at an angle which is greater than its critical angle of 42, it will be internally reflected like this. When it hits this other end, because it is also hitting this end at 45, this is how the binoculars also behave. Okay, now you are picking the object from here, but within there are lenses. Lenses are also incorporated with this prism. And you see, at the microscope, a single lens behaves as a hand magnifier. The magnifier we use in the biology lab to enlarge the size of objects. Now, the magnifier is such that when you put two lenses in place, the magnification power increases. Okay, so within this, there are lenses. Okay, there are lenses so that the object which is picked up here, the size of it, when the ray passes through this, will be enlarged, just as it is done in microscope. A microscope is just combination of two or more lenses. The more you add on to the lenses, the greater the magnifying power. So this is just like this, only that there are lenses which would help magnify the size so that if an object is afar, you can just be able to see it like this. Is that okay? So this is the principal design of the periscope, prism periscope, and then the binoculars. Binoculars. The next application we talk about is the formation of a mirage. Formation of a mirage. Please have these designs. If you haven't, okay, you can be asked to explain the principal application of the prism periscope and then the binoculars. So the next one is the mirage. A mirage is an optical illusion which occurs during sunny days or afternoon. And those who have actually taken a sojourn or walked through the desert before also have an experience of a mirage. You see, on the desert, because temperature usually of the day is usually very high, there's no water, but mirage formation often deceives them in such a way that when they view ahead, they see a pool of water. Being in an environment where there's no water, when you see a pool of water, or because of thirst, they will rush to quench their thirst, only to go or move on. And the further they go, the further the objects, what they see as water, also moves. So a mirage is an optical illusion. So they say that on the desert, they are actually confused so much by the mirage. How is the mirage formed? So formation of a mirage. What is seen as a mirage is as a pool of water is usually the image of the sun on the road. So if this is the sun, this is the road. You see, on sunny afternoon, the temperature of the road becomes so hot than the air layers above it. This is because the road is made up of stones, and stones have a very low heat capacity, meaning that when solids are subjected to small heat energy, they absorb it quickly. So on sunny afternoon, the road surface becomes so hot than the air layer above it. Okay, so assuming this is the first air layer, T1 is the temperature. The temperature of this air layer is so much because of its closeness to the surface of the road. Please, are you with me? Hello, are you there?
Yes.
The next air layer is this, of temperature T2. In terms of temperature, T2 is less than T1, or T1 is greater than T2. Then the next air layer is this. its temperature is T3. T3 is less than T2 and T1. So as we move, as we go up, what happens to temperature? Class, as we go up, what happens to temperature? Can somebody tell me? As we move up, what happens to the temperature of the air layer?
It decreases.
It decreases. And this is the reason why we say that the higher we go, the cooler it is or it becomes. Because as we are going up, the temperature of the air layer decreases. Now, air is such that when air is warmer, it becomes so light. So, the density of air, okay, decreases as a result of increasing temperature. So as we go up, the temperature decreases. But in terms of the density of air, this will be so light. So mu1, mu2, or let me use rho 1, rho 2, rho 3. As we go up, the temperature drops. But as we go up, what happens to density? As we go up, what happens to density? Class, I want somebody to help me. As we go up, temperature decreases. But what happens?
It decreases.
Look at it again. As we go up, temperature decreases. Okay, but what happens to density? Will it increase?
It will increase.
It would increase because when the air layer is so the temperature of the air layer is so much, the density drops. Okay, so this temperature is greater than this, but the density of this, okay, will be less than this one. So as we go up, temperature decreases, and in the same way as we go up, density increases. So temperature is decreasing, density is increasing. Okay, this is because when the temperature of air increases, air becomes so light. Now, the ray from the sun has to go through air layers of different densities. The first air layer is denser than the second, the third, on and on and on. So it is just similar to light ray moving from a denser medium into a less dense medium, the condition for total internal reflection. So the light ray from the sun will go through a layer of what? Decreasing density. And when it gets into one, because it is moving from denser medium to a less dense medium, it is refracted away from the normal. So it will bend. So it hits the road surface. When it hits the road surface, when the ray hits the road surface and reflects, it is now moving from, okay, less dense medium to denser medium. So it will deviate towards the normal. So an observer at a distance an observer at a distance, due to this progressive deviation of the. All right, I think let's discuss this and then. So an observer at a distance, because of the successive or progressive deviation of the ray from the sun, would see the image of the sun as if it's a pool of something on the road. Okay, so this, whatever is seen as the pool of water, is actually the image of the sun on the road. And this image of the sun is seen as a pool of water which is occurring on the surface of the road. So mirage formation is as a result of the successive or progressive deviation of light ray from the sun as it moves from a denser air layer, okay, to less dense air layer, and it is successively deviated away from the normal. When it hits the surface of the road, it is also successively or progressively deviated towards the normal. The reason for which you see this and then and almost this. It's not a sharp curve though, but it's as if it's like this. Successive deviation. This is how the mirage occur. Please, is there any question? Is there any question here? Hello? Hello?
No, please.
Okay, all right. So I think the network has not been so stable. So let us end here. Okay. Please, the assignment. Spend time to work on it. If you have concerns, WhatsApp me so I can have time to explain to you. So we'll continue once again next week. I'll be waiting for your assignment, please. All right. Bye-bye then.
Bye.
Okay.